Okay everybody, here's going to be a part 2 of this series on this Hewlett Packard wide range oscillator model 200 CD. I'm going to open it up again and I'm going to go ahead and check all the tubes in it, do a little more closer examination of a couple of things I thought about, and when I get through with the tubes and test them, I'll come back with a report, and then we'll move on to checking all the filter caps, and that'll be fun. And then once I do, matter of fact, what I'll think I'll do is I'll go ahead and check all the tubes, and then we'll just go ahead and power it up with the rectifier in place, and let's just see if it actually comes up and actually works, and then we can go from there. How about that? I think that'd be a better plan. So let me do my thing, and I'll bring you back. Okay, all the tubes checked good. Before I power this thing up, I decided to put a, if you remember, the line cord was cut off. The line cord was also rotten. So I'm going ahead and change the line cord, put a new line cord on it. But also the fuse holder was missing the cap, and I've got hundreds of these things brand new. Instead of just putting the cap in here, well, I guess it don't matter, but I'm going to see if I can put a new cap and fuse in here, put a new line cord, and then I'll get ready to power it up, and let's see how much this thing is working and how much it's not. So let me do all that and I'll come back. Alright, I went ahead and put a new AC line cord on there. Got the strain relief on there, connected neutral to ground, or actually green to ground. Here's your neutral. Then the black goes to the fuse holder. I replaced the fuse holder. It was missing the cap, if you remember. I just went ahead and put a whole brand new fuse holder. I got hundreds of them that I picked up here a while back. So I just put a whole new AGC fuse holder in there. So now I got to find according to the schematic, a 1.25 amp fuse. I got to find one of those real quick. And once I do that, then we'll hook this thing up to the dim bulb and put the meter on the some of the DC power points, and let's see how well this thing actually powers up, and we'll go from there. So bring you back. Okay. I have replaced the fuse holder, this guy, with a new 1.5 amp fuse. Is all I had. Time delay. I'll get the correct fuse once I'm done with this thing. But here's the rectifier circuit right here. The 5Y3 that's in there right now. This is the plates right here, as we talked about before. The output of the rectifier tube is right here. Looks like 215 volts. Filtered by C13A right here, and then goes through the filter choke, goes into C13B and C, 210 microfarads in parallel. So that would be 20 microfarad, and this is a 10 microfarad. So it's 3 10s, but it's a 10 and then effectively a 20 here. Anyway, I'm measuring right here with my voltmeter right there, which is this guy, As you can see, this is the output right here of the 5Y3. Comes straight to the filter choke, and from the filter choke goes to this capacitor right here. So what we're going to check first, I've got it hooked up to my dim bulb tester, which is here. You see the bulb over there. I got the isolated variable power supply right there. Everything's ready to go. So basically, I'm going to turn it on. Let me move this over just a little bit. I'm going to turn power supply on. I'm going to start from 0, work my way up. I'm going to watch the dim bulb. I'm going to watch the current, and I'm going to watch this voltmeter. This is the output of the rectifier. So here we go. Firing up. Firing up, drawing a little bit of current. We're going to stop at about 50 volts. Good place to start. 50 volts. Dim bulb tester is, I think that's lit pretty good. No activity on the DC meter yet. Let's bring it up. Bring it up to about 60 volts to see what happens. We're starting to see activity on the output voltage coming out of the rectifier. Coming up on almost 100 volts. We're at 150. I hadn't seen no smoke yet. About 162 volts right there. That's with 60 volts coming into the thing, going through the dim bulb tester, and the dim bulb tester is doing its job. It's still dim, so no problems there. So, no smoke yet. I really should have had this hooked up to my oscilloscope to see if there's any signal. Let's do that. I'll bring you back. I'm going to let it run at this level it's doing right now. I'll be right back. Okay, sorry about that. I went ahead and hooked the oscilloscope up to the output terminals through a ×1 probe. So my B+, as we're doing 60 volts input right here through the dim bulb tester, we have 98 volts of B+ coming out. I don't think I have a signal there. I got a little bit of something. Actually, there is something there. Let's sync this thing. Let's see if it changes. Doesn't change. I'm not sure what that is. Let's have a look at it here. I know you can't see me too good. Let's look up cursors. Let's do 1 second. So, now I'll tell you right now, that is 120 hertz coming on the output. Pure sine wave. It's not being generated by the oscillator. That 120 hertz is the output of the rectifier. So, let's continue. We're at 60 volts AC input with 100 volts. Here we go. I'm going to raise it up. I'm going to raise it up to 80. Dim bulb tester is not quite so dim anymore. My B+ is about 120. As you can see, it's dropping. Also, I have a change in the waveforms here. I don't see no smoke yet, but I also don't see oscillation. I'm going to kill that. Nothing yet. But my B+ is again dropped down to 93. Really shouldn't be dropping. Alright. I have a feeling we're drawing about 0.3 amps, if you can believe it. I'm going to run it up. I'm running up to 90 volts AC input. I'm going back to the current range. As you can see, the scope's gun. I have this oscillator set up for 1000 hertz. But as you can see, I'm still getting 120 hertz. But my B+, this is what's, my B+ should be higher. Okay? and the dim bulb tester is getting quite illuminated. That's not a good sign. Let's bring it up. Just bring it up to 105 volts. As you can see, my B plus is still not doing too good. It's at 91 volts. And you can see I should not be having a 120 hertz signal coming on the output. It's not good. Not good at all. Matter of fact, dim bulb tester is quite bright. I'm drawing almost 0.35 amps. That dim bulb tester is not quite so dim. Well, B plus should be higher than that. Oh well, let's carry on. I'm going to run it to about 125. That should give me adequate. I can tell you right now, boys and girls, that should not be there. Actually, we have a different signal now. Hey, look at there. That is the oscillator signal. See it varying? We have a tone coming out. We're still at 100 volts. Let's drop this thing. Yeah, it'll look right there. You see the ripple of the AC supply. That should be flat. I'll change the output. See, that is power supply. So, and I'm still at 99.8 volts. So what I'm going to do is I'm going to turn this off a second, unplug the dim bulb, and I'm going to go straight into just cord to respond. I'm going to do this again. This time we're going straight power. Here we go. I'm going to run it up to 50 volts. I wish I had my FLIR with me. You see how the B plus is dropping? I'm telling you, there's a bad cap in here. And nope, I'm not going to reform it. Let's bring it up. It's about 80. 80 gets, I don't want to do this too long. It's bad on that transformer. I don't know how much current the supply is actually drawing, but we're running. Let's turn this light off a minute. See what that rectifier is doing. Still at 120 volts. But look, it does oscillate. As you can see, I can vary it. That fine tuning knob with vernier is very sticky. I have to degrease it. There is a signal coming out of this thing. My B plus is low. I'm going to run it up full power. I'm not going to do this long. It's bad on that power supply transformer. See, my B plus is measured 175, and I'm drawing about 0.5, about 6.5, 650 milliamps of AC current on the input. But that B plus, I believe, is low. So should be 213. Let's see. Conditions of DC voltage measurement: line voltage at 115, which was the way we had. Amplitude 0, frequency dial, I ain't worried about that. Voltage is measured between indicated points and chassis with voltmeter. 120 mega ohms input resistance. So we definitely have something going on there, because that 215 measuring 175. Let's go have a look at the schematic. Alright, bear with me a minute, guys, because my Adobe Reader doesn't want to let me rotate things anymore. So anyway, I'm just going to rotate you guys. Hold on, you see. Anyway, there's the output of the 5Y3, 215 volts. Comes down to 190 through the L6 filter choke right there. So we're not even reaching this here. So I went ahead and turned the power off when I did not want to damage this tube or this transformer. So next step I'm going to do is I'm going to get in there and pull the pull the leads off these electrolytics and start checking for bad caps. So that's where I'm going next. Alright, I've got the first main filter cap disconnected. I've got my tester on there. This is all three sections. There's actually, if you look closely, let me move this lead out of the way. Ooh. If you look at this, there's 4 sections of this cap. 1, 2, 3, 4. However, if you a lot of these canned electrolytics, you'll see that this would actually be 4 sections of the capacitor. However, Hewlett Packard does things a little different. This is the internal ground that references these 3. So it's actually 3 capacitors and a ground. So this is a 10 at 450, this is a 10 at 450, and this is a 10 at 450, and that's the ground. So instead of using my Syncor resolver, we're going to use old school. I'm going to connect on the first section. Should be set up for 10. We're going to use this old boy right here. Old, trusty old C3 Heath kit. My capacitance test is on 1 to 50. Let's see, that would be this top scale right here. Okay. So I'll tune this knob here, the tuning knob. And actually, if I get right about here, somewhere in this order here, this eye should open. I'm all the way up to 50, past 50. See that? Nothing. Until I get way down. That's just what this thing does. So, let's check the capacitor. Completely open. You saw it yourself, folks. That section is completely open. Let's go to this section. Do the same thing. Nothing. Let's go over here to leakage. Oh, do it right. Now I got a little bit on that one. Did I do something wrong? Let's go back and see. Yeah, that one's open. Okay. Check this section. Make sure I didn't do something wrong. Acts like there's a filter there. Just go back and recheck the value. It's kind of like, One more time. That's not very good. Not very good at all. So let's see what the resolver says. Set it up for aluminum electrolytics. We're going to put in 10 microfarad, 450 volts. I'm going to go ahead and lead 0. Okay. I don't know about y'all, but when my little test lead slips off and makes that stupid little snap, that just really pushes my buttons. Alright, we're calibrating it. Calibrated. One thing I'm going to do before I do anything else, make sure that this capacitor has no charge. Good way to damage your fancy-hancy. Could just measure it with a voltmeter, I guess. The heat kit will discharge them. And I'm just making sure because I don't want to have to be making a repair video on a Syncor high dollar, very semi-sophisticated piece of equipment when I don't have to. Alright, back on that first section. So let's do the capacitor value. 36 or 37 picofarad. Check for leakage. No leakage, which corresponded to what that dude said. Matter of fact, let's turn that off. So let's go to the next section. Here we go. This one checks 4.3 microfarad. Let's check it for leakage. And it didn't like it right off the bat. Okay, third one. Check the value. That one is 6.5 microfarad. Check leakage. It didn't like that one either. So that is not the most bad capacitor I've ever seen, but it is bad and neither one of my testers like it. So I vote to replace it. So the next one I'm going to check, this little dude right here. That one, if you can see it good, that dude right there See the little squiggly coming out of it right there? That to me indicates a bad cap. Now I don't know what that cap is yet, but I will find it in just a minute. Anyway, I'm going to tack these leads back in on this capacitor, and then I'm going to open this one up and measure it. So bring it right back. Okay, the second capacitor, C14. This was C13, A, B, and C. This is C14. It's a 40 microfarad at 450 volts. So we're going to do the same protocol we did a few minutes ago. We're going to take the heat kit. Remember, this one is the same way. It's a 40. You see the two tabs, which normally these would be two separate capacitors, but in these Hewlett Packard devices, this tab is ground. This tab is hot, so we're looking for 40 microfarad. So we got this set on 0.1 to 50. So somewhere in here I should be getting an eyeball. And that eye is getting very weak. It's showing something up in the age of 50 there, but let's go ahead and check the leakage. Oh, hang on, I did something wrong. I omitted a step. You're supposed to tune the eye maximum, and you come over here to the power factor and adjust it maximum width. Then you come back, go back and forth. About as good as we get. Now, showing about 50. Now let's test it for leakage. Yeah, it has leakage. It should have opened up by now. Let it discharge. Just for grins and wiggles, before I subject my $3,000 something Syncor capacitance tester on there, I'm going to make sure it's discharged. Yeah, I'm being a little paranoid today. I thought I damaged it here a while back. It takes time. Here we go. Got to change the value. Got to go up to 40 microfarad. Here we go. Measuring 43.7 microfarad. Now we're going to do leakage. Look at there, 5.35 milliamps. The Syncor doesn't like it. Just for fun, let's do dielectric absorption. In other words, just testing the capacitor's ability to either be a capacitor or a battery, basically. But let's see what it says, just for grins and wiggles. 100% bad. It didn't like that one. So, if you're in doubt about these capacitors and you don't want to trust your equipment, all you got to do is look for this stuff coming out of the cap. That cap is bad. This one's bad. It's very flaky. This one's bad for sure. The only other one is this bad boy back here, underneath this filter. Underneath that filter, there's light. There's the screws to mount it. I'm going to have to move that filter to get to it. However, there's a power transformer in the way. So that's going to take fun, but hey, I'm just going to call them all bad. I'm just going to call them all bad. I'm not even going to subject y'all to the third filter. I mean, I've proven my point that things got bad filter caps. And I'm not a believer in reforming caps, because I assure you, when I got these capacitors to restuff them, there will not be any electrolyte in that first one I ordered. And the second one's got the guts coming out of it, which means it's just internally shorted. I mean, it's a resistor just about as much as it's a capacitor. So I'm not even going to fool with it. I'm just going to take it apart, gut it, and restuff it. Put it back in. You'll never know it got changed unless you look real careful. I've gotten real good at restuffing, and I'm not going to make another video of that on this. So I'm going to take, I'm not even going to worry about taking that other one out until I'm ready to change it. So anyway, the other thing that I wanted, let's look back at the schematic. Let's look at those 3 resistors, and let me show you what I'm talking about. Alright, let me turn my light back on. Let's see. These guys. This one is R30. Back up a little bit. This is R30. This is R31. This is R40. These 2 resistors, you notice they got the common rail right here. All 3 of these are common rails. Anyway, this is the minus part of the power supply right here, and I'll show you in a minute. Just remember, this has negative voltage on it. Okay, and I'll show you that in a minute. But this is R40, this is 31, and this is 30. And you notice that this one is mighty white. This one here is mighty dark. Wonder why that's dark? I'll show you. Remember, this is R40, the one that's dark. And this one is mighty white. Let me try something. Yeah, those should be all the same colors. So anyway, we'll first look at the schematic, but I want to show you one other thing, and when we're checking capacitors. Right here and right here, guess what? 2 bumblebee capacitors. What you want to bet they're bad? If not leaky, which bad and leaky is the same thing in my book. But let's, I'll check these later. I'm not worried about them right now. Want to order the filter caps. I'm going to go ahead and just change those out with some nice film caps. Anyway, remember, this is R30, R31, and R40. Let's go look at the schematic and we'll see what that is. Alright, let's see. Where's the schematic? I know, oh, wrong way. Sorry about that. Let's see, come over here. I learned how to do this. Okay, sorry about that. I had to get it right. Okay, here is here we go, right here. This is R30, this is R31. Okay. I'll just scroll down for a minute. Here's R40. So, you see that minus 135 right here? Scroll over a little bit. Let's come back over here and trace that over. Goes to the center tap of the power supply, secondary high voltage tap of the transformer. So look at here, going from the center tap to here to this plate of the 5Y3 rectifier. And this one is going from the center tap down to this plate. So the current's going to go flow through, you know, it's going to be the voltage is going to be rectified. Current's going to flow through the tube through L6 to the plus 190 right here. Okay, and that's going to go feed each individual stage. Okay, but you got to have a return. in a lot of full wave rectifiers. That's what this is. A lot of times this right here will be grounded. And in this case it's grounded but not directly grounded. It comes down, comes over here, goes through this 10K. Well, the voltage drop in this thing, well, this thing normally working, with everything working normally, the voltage drop from ground to here will be 135 volts. Remember, this resistor was really burned, really dark. Well, something's causing that. I haven't checked the values either. Let's go back. Let's go back. What were we doing? So right now we got that 135 comes up over here, and the first thing it does is it comes up here to these two resistors right here. That provides bias to the outputs section of this device, which is the 6AU5 that we checked a few minutes ago. That provides bias. Goes to an 8.2 meg resistor to the grid of the 6AU5, minus 25 volts. Here is the plate. Plate gets its voltage, I believe. Yeah, the plates are directly connected. No, it goes to a 500 ohm resistor right here. Plate voltages arrive from that. Let's see, 685. I'm looking at the schematic here. Yes. These are the plate loads for both 6AU5s. But the cathode of the AU5 right here. So it's looking for a ground, okay? So it gets its minus 3.2 from somewhere. So let's follow it. Comes back down, comes back through this L4 right here, comes through to this 3. What is 3? Well, just bear with me. Anyway, comes through here, comes through T2, comes right through here, comes through T2, through 1, comes out 2, and comes through here through R30. Goes back over, goes back down to R40. And the same thing here, goes through R31, comes here, comes to 2 of T1, comes out 1, comes out 1. Well, hang on a minute. See, that's on position 3. This is on position 3. I'm sorry, I missed a step. This other R31 comes through here, comes up here through 3 of T2, out 4, comes down here, and goes over to the cathode of V4. I'm sorry, V4. So these two resistors here are feeding negative voltage through these transformers here, depending on what your range is, and there might be something going on in there too. I don't know. I'm going to measure these resistors and I'm going to do a little bit more checking, but with this one here, I'm going to recheck this guy right here. They're probably all good, and they've probably been setting up on the bench for somewhere, just plugged in for a long time. But I have a feeling these capacitors right here in this section here, and I don't know where the other capacitors are. I hadn't looked at that yet. But anyway, I think the filter capacitors are the biggest problem. And then this 0.05 right here, that's that bumblebee. If that bumblebee is leaking, it's taking this 100 volts from this tube, or this 100 volts, and passing that 100 volts a little bit into this grid, upsetting the bias. When it upsets the bias, it causes this tube to conduct more,
because it's trying to make it more positive on the control grid. Well, if it conducts more, it's going to draw more current, and depending on how leaky it is, it could make it draw enough current to make everything, to upset the balance of the power supply and make it draw too much current through this resistor right here. That's my hypothesis. Whether it's true or not, I don't know, but now I'm curious about those bumblebees. So I'm going to shut the camera off a few minutes. I'm going to go check those bumblebees, and I'll report back to you, and we'll close this video up for the day. As I was, quick side note, hang on. As I was on a side note, all these people that talks about when they're working on radios and stuff like that, and they're hooking up the leads and all that, and they have to make a lead longer or join two components together, and they use the fancy little, you know, the little twisting processes that they use, and all these little wraps and special little pretty stuff. This is a factory installation from Hewlett Packard from 1957, okay? I'm going to show you what Hewlett Packard did. Look right there. You see that? That's the two half loops joined together and soldered. You see that? I'll come over here to the other one. Look right there. Same thing. That's Hewlett Packard from 1957. It has lasted just like that from 1957 to 2022 when I'm disturbing it. Matter of fact, it's proven pain in the butt to get loose. My point is, yes, you can make it all fancy schmancy and all that kind of stuff, but Hewlett Packard thought this was sound enough to use in their designs. It is not broken, it is not falling off, it looks decent if it's properly done, and if it's good enough for Hewlett Packard to do, I'm going to do it. Alright, back to checking caps. Wanted to show you guys, I checked these bumblebee capacitors. This one here, and this one here. First off, the Syncor didn't like it. But here, this one, I love this thing, but I'm used to this. I have it set up as a paper plus mica. Anyway, don't matter. Right now, this is where it checked a little over 0.06, which was comparable to what this said, 0.06 microfarad, which is a little high. They should never read that high, honestly. That's a clue. Anyway, I've got the leakage test set on 450 volts. This bumblebee is a 600 volt capacitor. But watch this. Look at the eye. The eye completely closed. Let's drop it down to 25 volts. See how it did on 25 volts? Let's drop it up to 150. He'll bring it up to 150. See? It did okay on 150. Yeah, look. That's on 250. Starting to show some leakage, isn't it? Look at there. So this thing does check it under power, under 600 volts. It did not like it. This thing, it agrees. It didn't like it either, and it gives me visual proof. Those caps are bad. Those caps are probably bad enough to put leakage into that circuit, imbalance that circuit, cause more current to flow. It quite possibly might have caused that problem. However, the filters are bad too. So it's getting new filters. It's getting new filters. It's also getting those two capacitors. Let's see. I'm not even going to bother with come on, I'm trying to rotate this screen again. I'm not even going to bother with checking any resistors. I haven't had to change a bad one in one of these HPs in the last 4 of them that I worked on. But anytime you see a bumblebee cap, you know, if you like the cap, that's fine. Take it out, replace it with a polyester cap. And if you like the cap, collect them as you pull them out. Make you a nice little display on something. Don't trust them. Especially these micas, I'm sorry, these bumblebees. Let's see if I can show it to you. I thought they had a barrel on there. Some of these bumblebees, they have a little barrel on the end of them, a little tab sticking out, a little tube sticking out, I don't know, about 30 seconds of an inch, something like that. Those are oil-filled capacitors, and almost every one of them are bad. But these are bad. I don't trust a bumblebee when I see it. And these did check bad. So I'm gonna have a feeling that along with capacitors may not have been causing this problem as I originally thought. I'm honestly believing now it's these capacitors here which were leaky, which was changing the bias on the output tubes right here and making the power supply draw more current, and which made, see, like this one was really leaky compared to this one. I've got one resistor here that's darker than, or lighter than the other, which means it's got really hot. Now the other thing is this one might just be a different color anyway, but I'm just looking right here at this is all completely just got hot. I believe those capacitors were at fault. Yes, I do. I think that's what caused this. I think this is actually, I think the 10,000 is probably good. I think the whole thing was this resistor right here giving problems because of the stupid bumblebee capacitor. So I'm going to change the filters on this because I know they're bad and they need it. And I'm going to change these 2 bumblebees on here because I know they're bad, and that is definitely, I believe, what has caused the problem. And then once I get all that changed, we'll put it back together. We'll recheck the voltages on the power supplies. We'll go into the range switches right here. We'll deox those or clean them up, get those terminals clean. We'll check the accuracy of this thing. Might clean it up a little bit, but I think it's going to live. I honestly do. I believe this. I believe we can make this another Hewlett Packard live again. And I just got to sit down and order the parts. So anyway, fun little adventure. So I just got to I don't have to stuff those capacitors, but I've gotten real good at it. These capacitors have covers over them. That's the hard part, is getting that cover off. Usually I just take an X-Acto and I just cut around the edges just enough, or I can take a heat gun to it. Heat gun, if you don't overdo it, you know, if you leave it on low settings a little bit farther away, let it heat up gradually, give it time to reabsorb into everything, it'll be a lot better than a direct heat gun right point blank at full blast, which won't do you no good. But I can get them off, I can get them changed, and I can get them restuffed, put them back in there, and it should look about like it did before I even opened it up. So that's my that's the status of this thing. I ain't gonna touch any adjustments on it. I'm gonna change the components that need to be changed, and we'll put it back on the bench. We'll check the amplitude. Basically the amplitude is not calibrated as far as, you know, like minus 20, there's a setting on there, a meter says minus 20 or minus 30 or whatever. you're going to have a minimum output and a maximum output. We're going to check that. Then we're going to check the dial accuracy of, you know, each band. Make sure that all that's correct, and if it tracks good and it's clean output, I don't have a distortion meter yet. I'm working on that. But if it tracks good, we're going to clean it up, button it up, put it on the bench, and another one that fixed. Anyway, thanks for riding along. Probably be a little bit before we do part 3, but it'll be worth it. It was fun working on this thing. So I've been off on at the camp, at a fishing camp, for a few days. So I was eager to get back to this thing. So now I know, and I feel confident this will make another addition to a nice addition to my workbench. Anyway, that's that. So we'll see you on part 3. Y'all have a good one. Bye.